Hi, in this video we're going to be talking about Markov chains and using diagonalization to show what happens to Markov chains in the long run. So we're going to be using this example here. We have 3 cities, and each year some percentage of each city's population will move to another city, and some percentage will stay. So the percentages moving to the other cities are given by this graph here. And I color coded it so that, for example, the city C is red, and all the red arrows are what happened to the people that were in city C, and it shows where they're going. So 75% of them are staying, 10% of them are going to A, 15% are going to B. Okay? The 3 numbers on the red arrows have to add up to 1 because in total, all of the people in city C have to have gone somewhere. Either they're staying in C, they're going to A, or they're going to B. Nobody's leaving the system. Right? So AN, BN, and CN are the populations of these cities, and we want to look at this matrix equation right here. So to get the next set of populations, I want to multiply by some Markov matrix. I want to multiply this Markov matrix by the old populations. And the Markov matrix is literally just the numbers in here arranged in the correct way. So they were color-coded over here. They're the same colors over here. So for city C, these are the people moving to city A, these are the people moving to city B, and these are the people staying put in city C. Each of these columns adds up to 1, just like each of the sets of colors individually added up to 1 before. So all the blue numbers added up to 1, all the green numbers added up to 1, and all the red numbers added up to 1. Alright, so I set up some initial state here so that the initial populations are just 30% of the total people in all 3 cities start out in city A. 40% are going to start out in city B, and 30% are going to start out in city C. It will turn out that these numbers don't matter. One of the important things to note here is I'm doing this as percentage of the total population. So these 3 numbers add up to 1. And if we were to apply this matrix M multiple times to the vector A naught, B naught, C naught, then we would still get that those populations add up to 1 because they're still representing the same group of people, and it's 100% of those people. Okay? Our goal is to figure out what's going to happen to this population in the long run. Okay? So where are these people going to end up? Or not necessarily the individual people, but in the long run, what proportion of the population is going to end up in city A, what proportion is going to end up in city B and city C. Okay? So we're trying to find the limit of applying this Markov matrix many, many times to this initial condition. So applying this Markov matrix n times to this is going to give us the values a sub n, b sub n, and c sub n. And if we want to take a limit as n goes to infinity of that, that's going to be the long-term behavior. Okay, so I've written here a diagonalization, so we still have this limit out in front. Forget about this 1 over 30 for now. The diagonalization of this matrix M is P, D, P inverse, and I've raised D to the nth power because the M here was raised to the nth power. That's why these entries have an n power in them. And this, you could also put an nth power right there, but it's just a 1, and so I left that off. Okay, so the inverse of this matrix right here needs to go here, and this is almost the inverse. It's just off by a factor of 30, so I pulled the 1 over 30 out in front. Okay, so the inverse of this matrix is 1 over 30 times this matrix. Okay, so these 3 matrices are what I need to apply to this vector here. And I'm not going to apply the matrices one at a time to this vector here because I want to show that this vector on the end really does not matter. So applying the matrix to the vector is the very last thing I'm going to do. I'm going to multiply all 3 of these matrices together. before I do that. And before I worry about multiplying matrices together, I want to look at this limit. So this limit looks a bit simpler now because the only place an n shows up in this is in the powers here. And we know what happens when we raise a number that's less than 1 in absolute value to the nth power. That number is going to go to 0. So what I've written here is I've taken the limit by exactly just replacing these two numbers right here with zeros. So they're now 0, everything else is the same. Okay. The next step I'm going to do is I'm going to multiply this fairly simple matrix here by this matrix. And what it's going to do is, well, when I take 0, 0, 0 and dot it with this, it's just going to give me zeros. And then dotting it with this is going to give me 0, dotting it with this is going to give me 0. And that's going to happen for every entry in the first two rows. So the result of multiplying these two together is going to be this right here. Okay, it's going to give me nothing in the first two rows. And in the third row, it's just going to give me 0 times negative 25 plus 0 times 18 plus 1 times 1. Okay, so we're going to get this 1, 1, 1 here. So that's fairly simple. And now I want to multiply these two matrices together. And I've done that here. So just to point out what's going to happen is when I take this first row and multiply it by this first column, we get 0 times 0 plus 1 times 0 plus 12 times 1. So we're just going to get a 12 there. And if I do the first row times the second column, I'm going to get the exact same thing because the second column is the same thing as the first column. And the third column is going to give us the exact same thing as well. So all three of these are going to be 12s. Okay. Very similarly, if I do this for the second row, I'm just going to get 0 times negative 1 plus 0 times negative 2 plus 11 times 1. And it's going to give me an 11. And the same thing in the second and third columns because, again, the second and third columns of this are the same. And finally, we're going to end up with 0 times 1 plus 0 times 1 plus 7 times 1 to give us these 7s here. All right, so this may all look like a coincidence so far, but I'm going to go back in a second and explain why we always get something like this. So we get this right here, and we're going to say that this applied to our initial condition. So we have the 1 over 30 out in front. And then I'm just going to distribute this in. So I'm going to say this is 0.3 times the first column plus 0.4 times the second column plus 0.3 times the third column. And that is just this. And because these numbers add up to 1, in total, this is just 1 times that column. Okay, so we have that 1 over 30 times 1 times this column is just 1 over 30 times the column. And then I've written the numbers here in decimal format. So most of the people are going to, or the plurality of the people are going to end up in A, slightly less people are going to end up in B, and then much fewer people are going to end up in city C. Okay, so one thing to note is why all three of these columns are the same. So all three of these columns were the same because we had a matrix of 1, 1, 1 here with zeros in the first two rows. Okay, any matrix right here multiplied by a matrix that looks like this is going to give you exactly the third column here repeated 3 times. Okay, so why do we get this 1, 1, 1? Well, that 1, 1, 1 is coming from this matrix times this 1, 1, 1. And I want to say that as long as we set this up in this manner, this matrix will always look like this. And what I mean by this manner is we choose the diagonalization so that we have an eigenvalue of 1 popping up in this third column. Okay? A theorem about Markov matrices is they always have an eigenvalue 1. I'll show that later on in the video. So we always have this eigenvalue 1, and if we put it in the third column, then this matrix, after we take the limit, is always going to look like this. And this is a little bit mysterious as well. We always have this 1, 1, 1 showing up down here, and that again has something to do with the eigenvalue 1. Although that's a little bit more complicated. I'll show that later on in the video as well. So we're going to always have this matrix exactly as is. We're going to always have the third row of this be all 1s, which means that this multiplication is always going to show up 1, 1, 1 with the rest 0s. And so we're always going to get this third column right here, 12, 11, 7 in this case, repeated 3 times here. So what is this 12, 11, 7? Well, this is the third column of my P matrix. Remember, the columns of this P matrix are exactly the eigenvectors of this transformation. So these could be scaled in multiple ways. I chose a nice scaling so that these were all integers. But the point is, this is some eigenvector with eigenvalue 1, right? The third column corresponds to this third column over here. So the eigenvector with eigenvalue 1 is the one that gets repeated 3 times, which is why before, when we were solving for the steady state is what we're finding here, we found a solution to ax equals x, right? In other words, ax equals lambda x, where lambda is equal to 1. That's an eigenvector with eigenvalue 1. I now want to show 2 things. I want to show that we're always going to get an eigenvalue of 1, and if we put it in the last column here, then in the last row over here, we're always going to get a row of all 1s. Okay, so to start out with, we're going to look at what happens to the characteristic polynomial when we take a transpose. And the proposition is that A and A transpose, A is an n by n matrix here, A and A transpose have the exact same characteristic polynomial and therefore the same eigenvalues. Okay, so let's take a look at A here. So I've written A in the standard way, just using double indices. So these are always A sub ij, where I is the row number and j is the column number for A. When we transpose this, the columns and rows will switch, and this A sub 2, 1 will end up over here, and the A sub 1, 2 will end up down here. But nothing will happen to the diagonal entries, and that's the important property of this. So here I have A minus lambda I. I've literally just taken a lambda off of each diagonal entry. And A transpose minus lambda I, we do the exact same thing. So I've switched all of the indices from, say, 2, 1 to 1, 2. So everything got flipped, transposed, and I'm still subtracting lambda off the diagonal. And the idea is that this and this, with the lambda subtracted off, are now transposes of each other. So that's what I've written right here. A minus lambda I, the transpose of that, is equal to A transpose minus lambda I. Another way of seeing this is, you could do this algebraically. The transpose can distribute into this difference here, and you can say that A minus lambda I transpose is A transpose minus lambda I transpose, but lambda I transpose is just lambda I still, because there's no off-diagonal entries. Recall this fact that if B is a square matrix, then the determinant of B transpose is the same as the determinant of B. Alright, and then we can use that fact to say that the determinant of A transpose minus lambda I, this is the characteristic polynomial for A transpose. Well, this is equal to this, because I've just replaced this matrix, which is this one right here, by something that it's equal to, right there. And then this is the transpose of something, so I'm using that as my B here to say that I can just drop the transpose. And so the transpose goes away, and we just get the determinant of A minus lambda I, which is the characteristic polynomial for A. So the characteristic polynomial for A transpose is equal to the characteristic polynomial for A. So Therefore, A and A transpose must have the same eigenvalues because they must have the exact same roots of their characteristic polynomial. Now we have this proposition here. If M is a stochastic matrix, like any Markov matrix would be, stochastic, remember, means that each column sums to 1, then this vector that's made up of all ones is an eigenvector of the transpose of M with eigenvalue 1. Okay? So here I've written down the format for M. This is very similar to the format that I just used for A and A transpose before. So M11 all the way down to MNN, and here this is row column. So 1n, row 1, column n. Okay, when we transpose this, all of the off diagonals switch with their counterpart, and now we're ready for the proof. So each row of the transpose of M must sum to 1. So remember, each column of the original sums to 1, but each row of the transpose is just a column of the original that's been transposed. And so the sum of the elements in that would still be the same because the elements themselves are the same. Okay? So just to write this down, for each I, from 1 to n, we're going to get m1i all the way up through mni added together must be 1. So the sum of each column, in this particular case, is the ith column of the original matrix. That sum is 1. And that sum is also the sum of the ith row in the transpose. Okay, so M transpose times this vector V is this M transpose times the column vector of all ones. Well, when we're multiplying this in, because all of these are 1s, we're going to get this times 1 plus the next one times 1 plus the next one times 1, right? It's just going to be the sum of all of these times 1. So we're just going to get the sum of each of these things, and this is exactly the thing that we're assuming is equal to 1, right? This first row all sums to 1. And so the first entry of the result here is 1. Well, the same thing's true of the second row here. Therefore, the second entry of this is 1, and true for every other row. All of the entries in this resulting matrix are 1, and therefore it is just equal to V again. Okay? So M transpose times V is equal to 1 times V, and that's exactly what it means for V to be an eigenvector of the transpose of M with eigenvalue 1. So now combining these two propositions, we get that 1 must also be an eigenvalue of M. So remember, M transpose has an eigenvalue of 1, and A and A transpose have the same eigenvalues. Okay? I'm not going to prove this fact, but I will just state that the multiplicity of this eigenvalue, lambda equals 1, is 1. And we're going to need it, but the proof is a little bit too complicated for what we're doing, and so I'm going to omit it. When I say multiplicity here, I actually mean the algebraic multiplicity as opposed to the geometric multiplicity of lambda equals 1. The algebraic multiplicity, remember, is the multiplicity of the eigenvalue as a root of the characteristic polynomial, whereas the geometric multiplicity is the dimension of the lambda equals 1 eigenspace. And saying that the algebraic multiplicity is 1 is also saying that the dimension of the eigenspace is 1. In other words, there's only one eigenvector corresponding to lambda equals 1. So remember, the last thing I'm trying to show is that there is a row of all 1s that shows up here. Okay, so this matrix that we're looking at here is P inverse. So remember, M is P times D times P inverse. So the D is without those n's in the exponent there. So I have that written here. So M is P times D times P inverse, and it's a diagonalization of M. So I'm saying a diagonalization of M as opposed to the diagonalization because remember, you can scale the eigenvectors to change the columns of P. You can scale them up to whatever, and it's going to affect the inverse, but it's not going to change the fact that it's still going to be a diagonalization. You can also switch which column is where, and that's another diagonalization. And I'm going to be a little bit specific here and say we only actually care about the diagonalization where we're putting our lambda equals 1 in the bottom right entry of D. And so we'll get to that in a second. So I want to look at M transpose now. So M transpose is the transpose of M, and M is equal to the product of these three matrices here. And remember the rule for transposing a product is that, well, first we need to transpose the last one, and then transpose the middle one, and then transpose the first one. So the order gets reversed. Okay? Another rule for transpose is that the transpose of an inverse is the same thing as the inverse of a transpose. Okay? And the main thing I want to point out here is that this matrix, this first matrix in this product of 3, is the inverse of this last matrix. And therefore, well, also I should point out that the diagonal matrix transposed is still the same diagonal matrix. The transpose does not change anything about a diagonal matrix. So that is just D again. And we have an invertible matrix times a diagonal matrix times the inverse of that invertible matrix. And this is a diagonalization of M transpose. So M transpose is equal to that, and it satisfies the diagonalization requirement. Therefore, the columns of this first matrix here, P transpose inverse, or I could think about this matrix here, P inverse transpose, the columns of that matrix are the eigenvectors of M transpose. Okay? So now I'm going to point out that we want to think about lambda equals 1 in the bottom right entry of D, just for convenience, so that we can have something to refer to. Then P inverse T, this matrix here, has an eigenvector corresponding to lambda equals 1 in its last column. So remember, these things are ordered, and if you have 1 in the last entry of D, then you have to have an eigenvector corresponding to 1 in the last column of your first matrix here. Okay, so again, lambda equals 1 has multiplicity 1 for a stochastic regular matrix. And we are going to say then that the last column of P inverse transpose has to be a multiple of this eigenvector that we've already found. So we don't know what scale it is. It could be all 2s or all 3s or all pi's, but it's some multiple of that. We can't have a different eigenvector there that's not a multiple of this one. Well, we're almost done, and I ran out of space, so I'm just going to say the rest of this. P inverse transpose has a bunch of 1s, or some multiple of this, so a bunch of the same number in its last column. Therefore, if I get rid of the transpose, P inverse is going to have a bunch of 1s, or a bunch of the same number, in its last row. And that's exactly what we wanted here. A bunch of the same number in the last row. Well, how do we know they're 1s? Well, technically they're not 1s, right? So remember that the inverse of P wasn't quite this matrix. It was this matrix times 1 over 30. So technically these 1s should actually be all 1 over 30. And whatever the same number you get as your last row, you can always factor that number out here, and you're going to end up with this exact same multiplication property. All right, that's it. Thanks for watching.